Okay, so we are looking at the algorithm for unification, which takes two patterns which may contain some variables and tries to find substitutions for variables which will make the two patterns identical. So, the task is to make them identical, and it calls a module called sub unify, and it takes two patterns. Let us just call them pattern 1, pattern 2, and a partially constructed substitution. Remember, the substitution is a set of variable value pairs, and the patterns are essentially, as far as we are concerned, lists, because we have converted, we are working with this notation of FOL, which uses this Charniak and McDermott notation of using list. So, a pattern is either a list or it is atomic in nature, and when it is atomic in nature, it is either a constant or a variable essentially. So, these are the different cases that you want to cater to when you are looking at pattern 1 and pattern 2. So, the first case is, I will just do a quick review, is that if let us say we have a function which tells us whether pat 1 is a variable. So, this will return true or false, or the other one, if either of them is a variable, then we call another routine called where unify, which takes the variable. I will just use this very informal notation. So, whichever is the variable, that is the variable here, and whatever is not the variable. So, I will just call it the other here and the theta essentially. So, essentially what where unify will try to do is to see whether this other, or let us just call it pattern, just to be consistent, it will try to see whether it can make an assignment of where equal to pattern. That is the goal of this, but before that we have to do a couple of tests. The first is that if where occurs in theta. So, I will use this notation belongs to theta. So, this basically means that the variable already has a value in theta. Somewhere earlier you encountered the same variable and you gave some value to that. Or I should really say not 2. So, if it already has a value in theta, then you call sub unify with pat hold and this pat that we are trying to unify and theta. So, essentially we want to be consistent. Let us call this so let us call this case A and let us call this A 1, then A 2 is if the variable belongs to this pat itself, this pattern itself. Then we will just return failure, and we will see an example of this as to why that happens. Case 3 is if they are the same, then return theta. You do not have to do anything, they are already the same, and otherwise, which is the case that we are really interested in, So, we add this one more substitution to the theta. So, this is what where unify does. Where unify is the part which really does all the work of finding a new value for this variable essentially. So, if either of them is a variable, then we just call where unify. So, if we go past case A, then so let me write this in different color. So, if you go to case B, then this is all that we have written there is on case A. Case B means neither of them is a variable. Now, so if one of them is a constant, then both must be same, which means that both the other one also must be the same constant essentially. And case C is that neither both of them are not variables and neither of them is a constant, which means both of them are lists essentially. So, we just put a test if length of pattern 1 equal to length of pattern 2, make a number of, I will just write this again informally, of recursive to sub unify with corresponding elements. Remember that both are lists. So, let us look at an example. So, let us say we have a statement which is in, remember in the implicit quantifier form, which says that if and then let us say the left hand side of the antecedents have two things which are joined by an and. Let me just use a lower case. So, let us say there are two predicates that we are looking for. One is S x. So, let us say S stands for something, S is a student x or something like that, and let us say the other one is some other predicate. So, there are two inputs or two conditions on the left hand side. B x let us say stands for bright x. So, we are saying if x is a student and if x is bright, then what? Then let us say for argument's sake that x is a female essentially. So, let us say f stands for female essentially. So, this rule says that if x is a student and x is bright, then x must be a female essentially. And let us say we have another pattern which is the following. So, we have these two patterns and if we want to apply this rule, then essentially we need to see if the left hand side of the rule which is underlined here matches this entire pattern here. If that is the case, then the left hand side matches, and then using the modified modus ponens we can conclude the right hand side essentially. So, let me ask you here, what is this cis ANISA here? In the statement, what is cis ANISA refer to? It's ANISA is a constant. What is cis? It must be a function. Remember our first order logic, the definition, that the arguments to predicates. So, S is a predicate which stands for, let us say, student. Cis must be a function which tells that it is a function of ANISA. So, let us say there is a function called sister, which means that everybody has only one sister, and so it must be a function. So, it is a term essentially, cis of ANISA is a term, and we want to do. Now, in this case you can see that case A applies. If you remember, case A basically says, sorry, not case A, case C, because they are both lists. So, we make corresponding calls with each of the elements in the list essentially. So, we make a call with and. In this case, case B will apply, and they are constants and they are the same. So, that will be accepted. Then the next element, which is this one, again case C will apply, because it is a list, right. So, we make corresponding calls. Then in the list, the first element is S, which is a constant as far as we are concerned. So, it is case B, and both are the same, both are S and S. So, it is fine. The second element has a variable, that question mark x is a variable, remember it is a universally quantified variable. So, now we make a call to where unify, and the call is with this variable and the other thing which is a pattern, whatever it is, in this case it is cis ANISA. And of course, I must have whatever the theta was, I must have that. Let us say theta is empty to start with, and we are just starting this whole process essentially. Now, this where unify will work fine. If you go through the cases, you will see that the case 4 or case C 4 will apply, because we will go through the test and we will find that none of the other tests are true. So, essentially theta will now become x cis ANISA. Let us say theta was empty to start with. So, we are finished with the second argument, which is that S of x. Now, we deal with the third argument, which is let me use a different color here, which is this with this. You can see that first both of them are lists, or both of them, neither of them is a variable. So, again case C will apply, and then correspondingly with the corresponding elements B will match with B and x. So, we will make a call here also with where unify x with cis ANISA. And now, the theta will already have this cis ANISA. Now, let me just rewrite this. So, with x with cis ANISA, this is a pattern, and theta which contains this assignment already x cis A ANISA. Now, in where unify case C 1 will apply, in the sense that x already has a value in theta. So, we will now make a call with these two arguments with a sub unify. So, maybe you should just work out this problem and see, you will see that yes, indeed we will find a match, and the unifier that we will find is essentially this. This is the MJU for both these patterns, and then we can infer that sister of ANISA is a female essentially. Let us look at one or two more examples to study as to why did we need those conditions, but let me begin with another one here. This example is from this book that I have told you about, Charniak and McDermott. So, let us say one of the facts given to us is on x. How do you read this in English? How would you say this? You have to speak a bit louder. Not something. Everything is on the table. Remember that the variable is a universally quantified variable in our implicit quantifier form. So, there is a for all x implicit here, which we are not seeing. So, this is basically saying that everything is on the table. And then the other statement we have is if on Big Bertha anything, then how do you read this? Big Bertha is a constant, let us say it stands for an individual, collapses is a function, on is a function, right. So, this says that if Big Bertha is on something, that something will collapse essentially. So, from this can we infer that the table will collapse? Logically, do not look at the representation that we have here. We are saying that everything is on the table, and then we are saying that if Big Bertha is on something, that thing will collapse essentially. From this we should be able to infer that the table will collapse, because Big Bertha is also on the table essentially. Now, if you want to use our unification algorithm, we will have to match this with the left hand side of the rule. That is always the case in modified modus ponens, right. So, the first case where both our patterns will apply, and then 3 recursive calls will be made, one with on, one with question mark x, and one with table essentially. The first one will match simply because they are constant, in fact they are the same constant. So, that is okay. The second one will give us a theta, which is x and the third call will end up making a, so it will call where unify, and if you go through the procedure, this in turn will call subunify. Why? Because x already has a value in theta and we are trying to unify x with table and x already has a value with theta. So, this call to subunify will be with Big Bertha and table, and this theta that we have constructed is already there essentially. What will this call to subunify return?
It will fail.
Why?
Because already x has been assigned Big Bertha.
No, but why will this particular call to subunify fail? This is case 2. If you look at the cases that we have, they are constants, but they are not the same constants. So, we will return fail. So, I may not have written that as part of the algorithm, but if they are not the same constants, we say that we cannot unify them. Obviously, you cannot make Big Bertha and the table as the same thing. So, we are not able to make the conclusion. So, what has gone wrong essentially? We started off by saying that we should be able to make this conclusion. So, any guesses as to what has gone wrong here? The variable names are same essentially. So, the problem is that these two are same variable names. If I had instead written, for example, instead of the first statement, if I had written this on y table, it would not have made any difference to logically to the statements at all, because all that statement is saying is that everything is on the table. If I say for all x, x is on the table, or if I say for all y, y is on the table, or if I say for all z, z is on the table, it does not really matter essentially. They are the same statement. It is just that because we use the same variable name, we ran into this problem essentially. So, the lesson here is let me write this here. We must use different variable names essentially in every statement essentially, and that term we say it is So, this is something that we need to be careful about. Whenever we are using universally quantified statements and they are different statements, we must use a different variable name, because once we put it in the implicit quantifier form, there is nothing to tell us that we are talking about different variables. Whereas, as long as they were within the universal quantifier, we could say that they are this variable is in the scope of this quantifier and this variable is in the scope of this quantifier, but we cannot do that here essentially. So, this is something that must be done, variables must be standardized apart essentially. So, let us look at another example also from this Charniak and McDermott book. This example has one statement which says this is a logical knot which is a unary operator. So, it will take only one argument, and that argument is a predicate C's. So, let us assume that C stand for being able to see essentially. So, C is x x stands for x can see x or x sees x, and not we put that, it means that x cannot see n x, and what is x? X is a universally quantified variable. So, this statement is saying that nobody can see oneself. And then we have a statement, another statement in our knowledge base, which says that if not sees So, I will use different variables name now y something, let us say. I will just use the example from the book. So, what does feet of x say here? No, it stands for the feet of x, but logically what is it? In the language that we are in first order logic, what is feet of x? Again it is a term, just like sister of x, feet of x is also a term essentially. So, we must be careful about that essentially. And so, what this statement is trying to say in some sense is that if you cannot see your feet, then maybe you should diet essentially like that. Now, the question is it the case that in other words, is this formula true? It should not be true, right, because all we have said is that you cannot see yourself, and the second statement says that if you cannot see your feet, then you should die. So, let us just see how unification handles this. We match this with this. So, the first one is again constant, the second one which is this much is a list which has got 3 components, out of which the first one is a constant, they match C's matches with C's, the second one they are variables. So, let us say that we substitute y with x and add it to theta, because they are both variables, you can simply replace one with the other, it does not really matter. Both will work. If you replace x with y as an exercise, you should try it out, or y with x you should try it out, they will work. But the third case is of interest. We are trying to do where unify x with feet of y with that theta that we have, but x already has a value in theta. So, you will end up calling where unify with y with feet of y and the same theta, and here our case C 2 will apply, no, case 1 C will apply. Or whichever the number is, I hope that is correct, and you will return fail essentially. So, the test that we had, that if the variable occurs in the pattern, then return failure, will catch this discrepancy here and will say that no, you cannot apply this rule, you cannot match this, unification will return failure. So, luckily for us, all of us do not have to go and diet essentially. So, just think about what you are trying to do here. We are trying to, in this where unify call, we are saying substitute y with feet of y. Now, what will happen? If you try to substitute y with feet of y, then inside that you will have to substitute it with feet of y, then inside that you will have to substitute it with feet of y. So, obviously, that is a never ending process. So, it does not make sense to do that essentially. So, that is why we have this test, that if there is a variable in a pattern, then just say that you cannot unify them essentially. So, next case of the unification algorithm, remember that we need this algorithm to do forward chaining or forward reasoning. So, in the next class we will come back to that and we shall look at the strategies that we can use for reasoning essentially. We will come back to forward chaining and the unification is just a module that we will be calling henceforth essentially.